All right, so I think I'm going to start right now. As I said, um, in our next major topic for buildings and air handling course, I've told you that we're going to do heat transfer, but I quickly realized that we are in Unit 2, I'm in Unit 24, Chapter 2, and that it is more about airflow than anything else. So I'm going to cover the fourth topic, which is airflow now. And if you have questions, don't be shy, put it in the chat or unmute and ask me. But this is going to be a rather longer um, lecture, and I want you to try at least and follow along in Unit 24, Chapter 2. So what we're going to cover in this lecture is air pressure readings, and this and other topics are a combination of information and concepts that we have covered before, but this way I will have at least one full lecture that brings everything together that relates to airflow. And if you are a note taker, you're going to appreciate that everything is in one place and we didn't let anything fall through the cracks. So air pressure readings, volumetric airflow, and duct system pressures, air velocity calculations. So we're going to do that. Airflow and temperature rise formula. This is something you're supposed to do in the field. Number 5 is very important in the field. Then you have blower fan types and uses. And then we have pulley and RPM formula. I am thinking that maybe we can cover the first 5 or 6 maybe today, and then number 7 we can also continue next week. So after I finish this, I will post a test on this, and the test is going to be 15%. And it will be probably due by the end of the course, last day of the course, basically. All right, so first things first, air pressure readings. Obviously, we have talked about gauge pressure, we have talked about absolute pressure, we have mentioned maybe mercury column. I remember explaining what it is quickly. We talk a lot about water column. We say inches of water column and whatnot. And then the concept of vacuum and how we measure that. We need to cover all this and probably a little bit more. So let's start with the whole idea of a barometric pressure. Barometric pressure is the atmospheric pressure. It's the same thing, and it's the pressure of air that simply presses down on us. If you look at the column of air that extends all the way to the outside of the atmosphere, you're going to find that each square meter of Earth's surface supports a column of air that is more than 200 kilometers high. Okay, put that in perspective. That's crazy. I know air is light, but if you have something that is 200 kilometers high stacked on top of each other, no matter how light that is, it's going to be very, forceful, and weighs about 10,000 kilograms, so 10 metric tons at Earth's surface. Okay, so this is what we're dealing with, right? This is what we call an atmospheric pressure, so we call it 1 atmospheric pressure, which is the same as 760 millimeters of mercury. Hg stands for mercury. And then this funny thing, measurement unit that people keep asking me, what is torr? Where does it come from? It's not even THOR, so we know what that is. But what is TORR, Um, and we know the Pascal measurement and we know the kilopascal measurement. So where does this torr come from? It is basically this. Barometric pressure can be measured using a barometer, a device invented in 1643 by one of Galileo's students, and his last name was Torricelli. I guess that's where Tor comes from. You know, it's a kind of tradition to name units of measurements in the honor of people who have major contribution in it. I am going to post this presentation on Blackboard as well as the video in case you guys want to go back and have a look at the details. So the first thing, as I said, is that, you know, what is the gauge pressure versus absolute pressure? One thing you need to understand is, like absolute temperature, absolute zero temperature, there is something called absolute zero pressure. So physically speaking, in physics, there is something called a pressure that is zero. That is the absence of all pressure, okay? So how do we measure that? Well, we have ways to measure that on Earth. It's not that difficult, but the idea is you make sure you know that there is a starting point, all right? And that starting point is what we call a absolute zero pressure. And that, remember that 14.7? And if you want to be very, very, very specific, it's 14.696. So 14.7 is the atmospheric pressure. That is the pressure I talked about, the barometric pressure, which is 10,000 kilograms of air pressing down on you, which we do not feel because our bodies are simply evolved to work and live and thrive under that pressure. So what does that mean to you? It means that for the test purposes, you have to always remember that PSIA, okay, and PSIG have a relation. They are a function of each other, all right? So 14.7 PSIA, basically 14.7 PSIA is equal to 0 PSIG. That's how it works. You need to remember this. And then you say 15.7 PSIA equals to 1 PSIG, and so forth. 16.7 equals to 2 PSIG, 17.7 equals to 3 PSIG, and so forth. Okay, this is what TSSA is going to test you on for sure. I'm pretty sure there was maybe a question about that also in the G3. They like to keep asking that question, making sure that everybody knows about PSIA. So the other question then is, what is mercury column? So to measure mercury column, what the scientists did is they took this test tube. This is regular chemistry class test tube, all right? And they filled it with mercury, completely filled it with mercury, and then they turned it upside down into a basin of mercury, okay, into a pool of mercury. What happened is that because mercury itself is extremely heavy metal, it simply fell down. However, the atmospheric pressure is pushing down on the surface of this pool, and by doing that, it is supporting the weight of this column here. That's how we know what is the pressure of the atmosphere. It is 760 millimeters, and it is measured in literal millimeters of mercury, which is also, as you know, called torr. So the pressure exerted by the atmosphere on the surface of the pool of mercury supports a column of mercury in the tube that is about 760 millimeters tall. Because the boiling point of mercury is quite high, there is very little mercury vapor in the space above the mercury column. So when we say this is vacuum, we mean vacuum, like that there is zero pressure, zero existence of substances here. There's nothing going on here. Okay? All right. The second most important thing you need to understand about the mercury or any column, it can be, water column, mercury column, doesn't really matter, is that all it matters is the vertical distance, not the linear distance, okay? This is the linear distance. This is the vertical distance. All it matters is the vertical distance. Why? Because we are working against gravity, right? And gravity is completely vertical or we consider it to be. It's not, but we consider it to be completely vertical. So in this experiment, if you take that tube, test tube, and start leaning it like the Tower of Pisa, eventually you pass that line, which is 760 millimeters, in which case you see that vacuum has disappeared. Because the pressure of air, of atmosphere, all right, can press that mercury all the way to that line. All right? If you are above that line, there will be vacuum. If you're below that line, there will not be vacuum because the air pressure around us will overcome that. Now, similarly, we have something called water column, and we've talked about water column over and over and over again. Now, if you look at this drawing here, a water column is in this drawing sitting on a 1 inch by 1 inch square. All right, so that's the footprint of the water column. And why do we do 1 inch square? Because the psi, the SI is square inches basically. And what is this? What is this column here? This column is 1 pound of water. So what we did is we took 1 pound of water and made the dimensions exactly so that the footprint is 1 inch by 1 inch. And then we looked at how high or tall that thing is going to extend upwards. Okay? Because we know it is 1 pound because of the psi, pounds per square inch. And we found that it is 27.72 inches. All right? That's the magic number that you need to remember. I don't like asking people to remember numbers, but in this case, you will need to remember. I think you should remember this whole drawing. Okay? This whole drawing, if you remember it, it is even better. I'm going to explain why. So in this drawing, here are the principles that guide this drawing. A column of water creates a pressure at the base of the column. Yes, because of the experienced gravity. The higher the column of the water, the greater the pressure. Yes, we know that. 1 pound per square inch is equivalent to having a column of water 2.31 feet in height. Hold on a second. What the hell? I was talking about 27.72 and then suddenly it says 2.31. Well, this is in feet, okay? And this is in inches. If you convert inches to feet by dividing inches by 12, you get 2.31. The good news is you're not going to need to remember both numbers. You need to remember only one. For some reason, it is impossible for me to remember this number. I don't know why. This is easier to remember, maybe because it is a little bit, I would say, symmetrical. 2772 kind of deal. I don't know. But this I cannot remember. I always take that and divide it by 12 to get to the feet of water height. All right? That's what I do. So the pressure at the base of that column of water would be 1 psi, 1 pound per square inch, right? And that height is very important, as you're going to see right now. So if we had a column of water that is this inches, which is also that feet, we would have a pressure of 1 pound per square inch at the base of that column of water. This is the base of all measurements that we work with. So let's have a look here. If you take, I'm just going to do quick math here. If you take 27.72 inches and you divide it by 12, then you have converted it to feet, and that's the feet of water column. Okay, but why do we convert it to feet? Well, the answer is because most of the time when you are dealing with hydronics, or when you're dealing with buildings that have 2, 3, 4, 5 stories, you are going to have some kind of pump in the basement, or a pump in the mechanical room that can be on top of the building, or it can be somewhere in the middle of the building if it is a high rise. And people will start talking about the head pressure. And head pressure is a funny way to explain, how high this pump can send water through that pipe. All right. So when we say the head pressure is, this many feet of water, what we mean is, let's say the head pressure is 5 feet of water column. What we're saying is this pump can send that water in this pipe 5 feet high. Obviously, that's a very small number for any application that involves buildings. So most of the time you're going to see pumps that are gigantic, and they have superpowers, such as sending water into the pipes as high as like 10, 12, 13, 15 and more stories upwards against the gravity. So that's why this number is important. This number is important for gas technicians because we do measure the gas pressure and air pressure in inches of water column. But once you start talking HVAC and hydronic heating, which is coming up in the summer, you have a hydronic heating course in the summer, you are also going to talk about feet of water column. As long as you remember this formula, you are good to go. And again, you don't need to memorize both sides. You can just memorize one of them, whichever works for you. All right. So I have a question here saying, doesn't atmospheric pressure exert its force in all directions within a small given space? The answer is yes. Atmospheric pressure exerts its force downwards, not in all directions. It exerts downwards because it's a direct result of gravity. So gravity pulls down on the mass of air, and therefore it's like your weight, your body weight. Your body weight doesn't exert its force in all directions. It exerts its force in the vertically down. What you're referring to as atmospheric pressure exerting its force in all directions, we call that static pressure. So static, and I'm going to explain what static pressure is basically. Just hold on, and we're gonna get there. Okay, so this is exactly why we need to talk about inches of water column. So here are 3 instances of the best manometer that have ever existed on Earth. The best manometer is the YouTube manometer. It does not need calibration because it is self-calibrated by gravity, for God's sake. And if you ask me, I will always use a YouTube manometer and never use a digital manometer. But sometimes you need to, go with the specs of whatever the customer is asking. So how does this work? If there is, okay, so one thing that you need to know is one port, we call those openings ports, okay? One port of the U tube manometer is always open to the atmosphere. Not always, but when we're measuring a single point pressure as opposed to differential pressure, is always open to the atmosphere, and the other one is is sensing that pressure in the membrane or whatever. It doesn't matter at this point. So in this case, you can see that this U, is a liquid, and the liquid is simply undisturbed. Now, if we keep adding water or other substances into this container, what will happen is this weight is going to push down, and it will simply disturb that U-shape liquid, and it will create an uneven two levels that are not even, and the difference between those two levels is the pressure you're reading here. All right, so in this case I'm reading 2 inches of water column, and similarly I added whatever substance that is, and I started reading 4 inches of water column. So as long as you're reading 1 to, I would say, 5 inches of water column, a U-tube manometer is the one of the best measuring devices that there are. So this concludes our air pressure measurements. If you have any questions, you can ask now, or I'm just going to continue with the volumetric airflow. Right. So in terms of volumetric airflow, you have heard those units over and over again. Airflow is ordinarily measured in cubic feet per minute, CFM. For example, rule of thumb for cooling systems is that every ton of cooling requires 400 CFM of airflow. Did you get that question on a G3 exam? No? Okay. You are going to be asked this on the G2 exam. On the G2 exam, the question would be, how many CFMs is required of airflow is required for an air conditioning system, like residential A-coil air conditioning system? And the answer is 400 CFM. The other question will be, how many cubic feet per minute of airflow is required for a heat pump? Okay, so heat pump and air conditioning are going to be two different things. For air conditioning, you need 400 CFM. For heat pump, you need 450 CFM. Obviously, this is not engineering. This is a rule of thumb, but you're going to be asked on the G2 exam, and well, guess what? 3 marks. Okay. Now, what we need to work on in addition to the pressure is the flow rate. All right. Yes, we need to do the flow rate, but there is one more thing we need to do, and that is finding the velocity of the airflow. It's called airflow rate. Okay. So the velocity, why is it important to know the velocity of the airflow? Because of comfort in terms of feeling a cold draft, for example, or because of the noise. If you have high velocity, you have high noise. That applies not only to airflow, but it also applies to water flow, to refrigerant flow, and everything like that. But what we care here is the velocity of air going through a ductwork, okay? And that velocity in many cases should not exceed 650 to 750 to not create a noise or discomfort. So this rule here says that velocity is equal to airflow in CFM divided by area of duct. Make sure it is in square feet and not any other. So this is what this rule is saying, and we're going to do exactly that. We're going to do exactly that. Okay. Here's an example. If the blower in a forced air distribution system moves 1200 CFM of air through a 24 by 12-inch duct, what is the airflow velocity? Okay, again, velocity equals to airflow in CFM divided by duct area in cubic or square feet. Now, mind you, this is in inches, right? That's important. So most of the time you are going to be given the dimension of the duct in inches because that makes sense. We don't measure the duct dimensions in feet. It's simply too big. Why don't we do that first? Why don't we do the area of the duct? So duct area is equal to 24 times 12 inches. And if we multiply that, let me simply multiply that here. 24 times 12, oops, is 288 inches squared. And how do you convert square inches to square feet? But how do you do that? I'm gonna come back to that, Christopher. You don't divide it by 12. No. Okay? You divide it, correct. You divide it by 12 squared. Yep. By 12 squared. Don't forget that square, which is 144. And guess what happens when you do that? Duct area then equals to 288 divided by 144. It's 2 square feet. Oops, square feet. That's it. That was the whole measurement we're looking for. Now, here's the thing. We have a smart student there, as you can see in the comments, that says, well, isn't 24 2 feet and 12 inches 1 feet? Why don't we do that to start with? Just multiply 2 feet by 1 foot, and that's it. And yes, that's what you do when you have been working on this formula for long enough time. So in this case, we have calculated duct area in square feet to be 2, and the CFM is given here. The CFM is given here. It's 1,200. And guess what? The answer is 600, right? Feet per minute. That's your speed, or velocity. I shouldn't call it speed. Don't you call it speed. Call it velocity. And this is, by the way, this is acceptable. This is 600 is acceptable. It's very nice, quiet airflow. It could be, up to 750, where you start hearing air making its way in the duct. All right, we got that? Any questions? No? This is important. I'm gonna ask you about this, right? Just let you know that I am going to ask you about this. All right. So now I'm going to advance to duct system pressures. Duct system pressures. And this is probably something that you don't necessarily need to remember, but you do need to understand, because so much of your HVAC training will be based on airflow. And if you do not understand, total pressure versus velocity and static pressure, you will have to memorize a huge amount of information. But if you understand how this works, it will come down to, associating ideas and not memorizing. So let's talk about the pressures. Why do we say pressures in plural? Because two different types of pressures, that is static pressure and velocity pressure, pressurizes a duct system. The sum of these types is called total pressure. So let's have a look at this very simplistic kind of flow and pressures. And to be honest with you, whatever this fluid is, it doesn't matter. This fluid can be air, it can be water, it doesn't matter. It's the same rule. So you're going to find that we use only two ways, physically, two connection ways to measure the pressure. One is going to be perpendicular opening, a side opening to the pipe or the conduit that is carrying the flow. And the other will be such that it is facing head on the direction of the flow. Okay? So in other words, we're going to measure the pressure perpendicular to the flow direction, and we're going to measure the pressure parallel to the flow direction. You're going to see that only those two ways of measurement exist. One thing you need to remember is if you do that, you're measuring total pressure. Okay? You do need to remember that. If you do that, you're measuring only static pressure. That's number one. Number two is total pressure is equal to the static pressure plus velocity pressure. All right? This is, okay, I'm going to repeat the two, or let's say the three concepts. The three concepts is, number one, there are two ways to measure pressure. One is perpendicular at 90 degree to the flow direction, and the other is parallel to the flow direction. That's number one. Number two, the one that is perpendicular is going to measure the static pressure, and the one that is parallel is going to measure total pressure. That's number two. Number three is that your total pressure is the sum, is the simple addition of the two values, okay? And you're going to see why that is extremely important. So in other words, if you take, if this is a duct, a manometer connection is positioned perpendicular to the walls of the duct or at 90 degree to the airflow. It senses only outward or static pressure. We talked about this, right? So do you remember the manometer, the YouTube manometer? It's the same concept here. So this disturbed levels, uneven levels of liquid is going to indicate the pressure, which is in this case static pressure. All right? Now, there is a common misconception that you're going to see all the time. All right? It is wrong, but you're going to see all the time because some things are like fake news, I guess. I don't know. So static pressure is air pressure in a duct at right angles to the direction of flow. True or false? I'm going to say it is false. Okay. Static pressure is measured at right angles. Yes, that is correct. It doesn't mean static pressure applies only to the walls. Static pressure applies also in this direction, and that direction, and that direction, and that direction. Okay? Remember, there was a question about atmospheric pressure exerts its force in all directions. This is what I was talking about. Pressure, static pressure exerts itself in all directions. But when we measure it through an opening that is perpendicular to the direction of flow. All right? Don't forget this. And every time you're going to hear this, just shake your hand, agree with whoever is saying it, and just in your head say, yep, sure. It's false, but whatever you want to believe in. And here's the absolute, proof of what I was saying. It's right here. This is word for word from your textbook. All right? So this is from your textbook, and this is from your textbook. So you're going to see how it contradicts itself. If static pressure is pressure in the duct at a right angle, if that is true, so this is not a static pressure, right? All right. What does it say here? Velocity pressure is the air pressure in a duct that parallels the direction of flow. All right, I'm going to agree with that. I'm completely going to agree with that. What does this say though? Static pressure and velocity pressure are pressing here. Uh-oh. I thought static pressure presses only perpendicular. No, it doesn't. We measure static pressure perpendicular, but it also exerts parallel to the flow direction. Are you following me? This is very important. But why is this important? Well, here's the thing. You cannot measure velocity pressure, guys, with the technology we have. Instead, we measure total pressure. Remember, this was total pressure, right? We measure total pressure, and we measure static pressure, and we simply take away static pressure from the total pressure. How? Well, isn't this static pressure and velocity pressure? So isn't static pressure pressing in this direction? Yes. Isn't static pressure also pressing in this direction? Yes. Don't these opposite forces cancel each other? Yeah, they do. It's genius. They simply cancel each other. They are equal forces. Static pressure here and static pressure here are equal, roughly speaking. So when the force is going in this direction here and the force is going in this direction here, they simply cancel each other. And we are left with velocity pressure. Do you see what I'm saying? This is one of the most genius ways to measure velocity pressure. It's simply you're measuring it indirectly, but you are measuring it. Here's the thing. The air flows straight into the inlet of the probe and senses total pressure. The second probe is sensing only static pressure, canceling out the static portion from the total pressure. The manometer only registers the true velocity pressure. We get that? All right. And here's the pitot tube. If you look at the pitot tube, you see that it has an opening at the tip that opening goes all the way in like that. All right? And there are openings here which measure the static pressure. Here, it measures the static pressure. So it measures total pressure and static pressure on both sides. And then this opening measures only static pressure. So the static pressure measured here and measured here cancel each other, and we are left with simply velocity pressure. This is a presentation of how it works. This is the pitot tube, okay? It has two ports. One port is measuring the total pressure, and the other port is measuring the static pressure. Whatever you left is your velocity pressure. Why is it important? Well, because at one point in your career, you are going to do this. Air velocity calculations. At one point in your career, you are going to do this. I am sure 100%. What is air velocity calculations? Well, you remember we had a relationship between the velocity and the airflow and size of the duct? Yeah, we had that. We just did that. So if you can measure the velocity pressure, okay, and you have this constant in the imperial system, you can simply get the feet per minute. If you get feet per minute, you can literally calculate the CFM. CFM is a critical thing to calculate. So if you start by measuring the velocity pressure, then calculating the air velocity, you will eventually end up with calculating the CFM, which is absolutely very, very important. Here's an example. By the way, we're going to apply this formula where V is the air velocity in feet per minute. This is a constant, and this is your square root of the velocity pressure. So let's take an example here. Determine the air velocity wherein, who put that word in there? Shakespeare probably. The measured velocity pressure is 0.02 inches water column. Can we do that? All right, let's try and do that. So we're just going to simply say 4005 multiplied by velocity pressure of 0.02, right, inches of water column. Remember, in here it said inches of water column, right? Velocity pressure measured in inches of water column. Always make sure that you don't need to do any conversion of units. So if I do 0.02 squared, can I do it here? No. Can I do it here? Yes, I can. Square inch of 0.02 is 0.1414 multiplied by 4005. I'm just going to multiply that by 4005, and I'm going to get 8.95, right, feet per minute of velocity, airflow velocity. This is air. Yes.
Yeah, like 566.
Let me hold on a second. Let me have a look at it. Okay, so going back to this calculation, which I did wrong last time. So if we multiply 4005 by 0.1414, we get 566.3 feet per minute. Okay, that's air flow velocity. The good thing about this is now if I know the size of the duct that this air is flowing in, I can tell you what's the CFM, right? That's the whole idea of it. That's the whole idea of it, because we said that velocity, a few slides back, we said that velocity was the CFM basically over the area of the duct, remember? So that means that CFM equals to velocity multiplied by the area. So in this case, velocity, let's just say 566, okay? 566 multiplied by whatever area of duct I have. That gives me the CFM. This is very important. Very important. The more you start troubleshooting HVAC in the field, the more you're going to realize that we have more problems in airflow than in any other mechanical area. That's at least my experience in the, and I think a lot of mechanics agree with that, especially in the commercial. In the residential, it's easy to target airflow. You look at the filter, you look at the blower, you look at the A coil. You can put things in, together quickly in terms of troubleshooting. But in commercial, you're going to find that airflow is absolutely very important and critical. All right. Now, we're going to do another calculation, and do please keep up the work of making sure that my calculations are correct. This is probably the most important calculation that you need to do when you are troubleshooting a furnace. How on earth are you going to figure out whether or not the troubleshooting of the furnace that you did, is good or not? So most of the time, what happens is you get to the furnace, you can read. So for example, I'll give you an example. A customer says, the furnace is working, but it's not, the room temperature is not reaching the set point. It is -20 outside. They set the room temperature to, for example, 21 degrees Celsius, and the furnace is running, periodically running, stopping, but it is not going over 18 degrees. And this is something recent. The furnace has been working for 8 years and there was no problem, right? So why is it suddenly not reaching the set point? So you go there, and the first thing you should suspect is what? Airflow. Why? Because if the filter is dirty, or if the A coil is dirty, what will happen is there will not be enough airflow. Think about the furnace generating 80,000 BTU, and it requires 2,000 CFMs, and you're circulating 1,200 CFMs. You don't have enough air to go through the heat exchanger to pick up the generated heat. This will result in buildup of heat in the furnace, and that will result in tripping the high limit switch. If the high limit switch is automatically reset, it will turn into the furnace running, overheating, stopping. Before it delivers enough heat, it will stop, and then the high limit switch will reset, and the cycle starts all over again. Am I clear? This is something going to be, one of your troubleshooting instances. So how do you go about finding out what happened? Here's a simple example here. This is what you're going to calculate. Why? Because I just told you it is 80,000 BTUs per hour. It requires 2,000 CFMs. Okay? And how do I know that? Well, I just read the rating plate and I looked at the installation manual. It says 2,000 CFM. Now the question is it delivering 2,000 CFM? I don't know. How am I gonna know? I'm gonna either use, the previous example, use a pitot tube and measure the velocity in the duct and then turn it into CFM, or I can use this formula, which is as powerful as the formula before. All right, so this is 80,000 BTUs per hour. Perfect. Temperature rise. Where do you see the temperature rise, and what on earth is temperature rise? Well, first of all, there is a design temperature rise and there is measured temperature rise. So for example, If you look at any rating plate of a furnace, you're going to see any rating plate, you're going to see that there is a design temperature rise. It will say 45 degrees Fahrenheit or 75 degrees Fahrenheit, and it is simply saying that the air coming in, the temperature of the air leaving minus the temperature of the air coming in, okay, is the temperature rise. So how many degrees Fahrenheit you are increasing the temperature of the air as it passes through the furnace versus how much you should actually do it. All right. So let's say, by the way, this must be measured, not taken from the rating plate. Absolutely important. This is not the one that is taken from the rating plate, okay? This must be measured. All right. And it is simply leaving air temperature minus entering air temperature. So basically this is supply air, this is return air. We know that already as far as furnaces go, and this example is about a furnace. Say, for example, your temperature rise that you measured came up to be 86 degrees Fahrenheit, and this is 80,000, all right, and this is a constant. Let's see how much is the airflow. So airflow in this example is going to be equal to 80,000, okay, this is 80,000 divided by 1.08 multiplied by 86 degrees Fahrenheit. So I'm going to do the math. I'm going to do it very carefully this time. 80,000 divided by 1.08, also divided by 86. It is a despicable 861 CFM. Do you think you have a problem? We were asking for 2000 CFM. We got 861 CFM, if my math is correct. That is a huge problem. Huge, huge, huge problem. It's not even close. So, well, that's something that you're going to do in the field. I know I have done it just to prove to the customer that, hey, we have a problem here. And that you need to remove those books and, you know, the shelves and whatever is covering the air register, because the filter was clean, but the air outlets in the floors on the second floor and some in the kitchen were completely covered by stuff. And the customer was like, oh, it doesn't matter, I just covered a few of them. Yeah, you covered a few of them. Sure, you covered a few of them. Anyway, so this is something that is very important to do. Now, I know I have been talking for almost an hour, and you are probably, your brains are probably mush by now. Oh, so I have a question saying that can low CFM be an indication that the motor capacitor is bad? If it has a running capacitor, yes, but not this bad. Like this disparity between 2000 and 861 indicates more than just motor capacitor. It can indicate you know, closed air passages and dirty filter or dirty air aqua. All right, so I'm gonna just introduce you to the This was number 6, blower types and uses. I can go through this, but I'm going to ask you whether I should right now because I've been talking for a good 1 hour.